So section 2.3 is primarily concerned with displaying data, displaying information, but it's going to start out with a little review type problem. One of the things we mentioned that was a big concern the other day was voluntary response. So suppose you have a large voluntary response sample consisting of weights of subjects who chose to respond to a survey posted on the internet. Can a graph help to overcome the deficiency of having voluntary response data? What do you think? Could? All right. Someone got a different opinion on that one? Could make it worse because it could look authentic and like, ooh, they really know what they're doing. They got this cool graphic. But there's really no amount of statistical torture that can save bad data. If it's bad data, it's just bad data. And unfortunately, in the computer age, a lot of times people suffer something that in college I used to call garbage in, gospel out. You give them any kind of data, and once it goes through a computer, people are like, ooh, this is what the computer said. But if it's garbage data, it's garbage results. And even the author says something similar, says, if the sample is a bad sample, such as one obtained from voluntary responses, there are no graphs or other techniques that can be used to salvage the data. If it's bad data, it's just bad data, so stay away from it. Now, once you do have some data, the question is, what are you going to do with it? You want to display it. And there's a couple of good ways to display it and a couple of bad ways to display it. Let's start with a couple of examples of some bad things to do. And we'll start that with some nausea results from a clinical trial. So what you see here in these graphs are the percentages of people experiencing nausea who got the placebo versus who got OxyContin. So, but it looks like some pretty dramatic results, right? OxyContin looks really, really bad here. Or is it? What's the difference between these two graphs? And why is one of them misleading?
One starts at 10%.
Yeah. This one starts at 10%. It doesn't start at 0. So what it's doing is that it's exaggerating this gap. So this is the same problem we saw last week, is that you're not starting at 0. If you start at 0, there's still a gap. You're still experiencing more than twice the nausea here that you get here. But, gosh, this looks like 8 or more times the difference. So, got to be careful with graphs that start at something other than 0. It's not to say that you can't have them. They're fine. You just got to be careful. Let's go down to a misleading graph that relies on pictures. In 1970, 37% of U.S. adults smoked. That percentage had dropped to about 18% in 2013. Roughly speaking, at a first pass, if you compare this divided by this, roughly speaking, rounded off, what would you get? Yeah, about 2. All right, so this is about twice as much. Is this cigarette here, is that twice as big as this one? Oh, well, the thing is, it might be twice as long, but it's also twice as wide. So overall, you're getting 4 times the area. So this picture, if you were to measure the area, height times width, and compared to this one, you're getting 4 times the area. 4 times the area is not representative of 2 times the number of smokers. It's misleading. I mean, this looks like, gosh, we've cut it down in quarters, and really you've only cut it down in half. So again, misleading. Now, there are a lot of good examples of statistics and different ways to display statistics. I can't remember the last time I picked up USA Today, but they always seem to have these snapshots, right, with a little pie chart telling you the percentage of people who like to do this or that out on the lakes, etc. And those are in a pie chart. And so what you're doing is you're filling in this, coloring it in with enough to represent the proportion of people who like to jet ski or who like to sailboat, etc. Oh, stolen boats. Well, I think of it as, let's just think of it as things you like to do rather than getting ripped off. We're going to positive spin. This is a kinder, gentler class. So that's one thing. You can do a pie chart. You can do a frequency polygon. So in our previous sections, we started dealing with frequency distributions and frequency histograms. Well, going back to one of our data sets, problem number 6 from section 2.1, with all these class midpoints. So the class midpoints can be used along with a frequency histogram, so 24.5, 34.5, etc. You can plot these points together, the class midpoint and the frequency, to get a frequency polygon as opposed to a frequency histogram. If you did that with cumulative frequency, it'll look a little bit different. You can work with a relative frequency, but there's tons of places that you can do this. Other information, other ways to display data. There's a dot plot. And this one's a little bit more of a personal example. I like to do a lot of open water swimming, and my phone keeps track of the data. Interestingly enough, it displays it, amongst other things, as a dot plot. Now, one of these kind of stands out. And this simple dot plot does highlight one interesting little event here, and that is this one. This one was a significantly faster swim than a lot of the rest of them. A lot of the rest of them are down here. So what was different about this one? Well, you can investigate that one and find out what was different. And in this particular case, it happened to be that I wore a wetsuit that day. It was really cold. And a wetsuit gives you more buoyancy, so you're a little bit faster. Actually, a lot faster. So that's a dot plot. Stem and leaf plots are handy. I'm not sure I can demonstrate one very easily on that. So let's go to this way, this one, displaying data. Nice visual representations. Who's ever heard of a megalodon? Anyone heard of a megalodon? What is it? Prehistoric shark. I remember seeing a picture of this when I was really, really young and going, that's fake. But it's not. Megalodon was this massive shark. Calling it a shark seems like an understatement because it was huge. There's my son standing in front of it when we were visiting Cranbrook. This thing could swallow my son or me without even a burp. It was huge. And a nice, better graphic of this to display the size is this. So this one you see the tallest, or an average sized man, and the largest great white. Compare that to the lower and upper estimates for the size of Megalodon, and wow, this thing was big. I would not want to be on the ocean in anything less than the Queen Mary if that thing was swimming around there. But giving something for comparison to size helps out. This tooth was like 6 inches big. It's huge. Earlier we said that you have to be careful about displaying something that doesn't include a 0. Here's a look at average temperature data in Oakland County starting in the year 1900. Now I've included 0 on this, but what that did for me is it kind of compressed things. So does it look like there's much of a trend here in the temperatures? It's tough to see because everything is compressed on the y-axis. So what if I allowed myself to start at someplace other than 0? Now does it look like a trend in the average temperature here throughout the 20th century? Absolutely. Later on in this course, we'll learn to fit a regression line that'll make that trend a little bit more visible. But yeah, and you can see that in the 100 years of the 20th century, the average temperature in Oakland County went up almost 4 degrees. So that's a significant increase. Box plot is another novel way to display some things about your data. on the end of this. Sometimes we call this a box and whisker plot. At the end of the whiskers is the lowest value of your data set, and then the highest value. And then this one right here, the 98.4, is what's in the middle. It's going to separate the top half from the bottom half. And then these numbers separate those halves. So in the bottom half, this separates the lower 25% from the next 75%. And then this number separates the top 25% from the bottom 75%. And so on. This one's amazing. In fact, I heard a new term for this. It's called an infographic. And it talks about Napoleon's retreat, Napoleon's advance and retreat from Moscow. Because it shows so much information about that debacle. He started out with an army of over 400,000 men. And that's represented by the thickness here of this line. Now, as he marches toward Moscow, what's happening to the thickness of this line? Getting thinner and thinner, right? So what happened was that he had troops that weren't dressed up for winter marching on Moscow during winter. So not only do you get the size of the army, but along the bottom you see the dates and you see the average temperature for the day. And it was really, really cold. So his troops advance on Moscow, and the Russians keep on falling back and burning up the earth in front of the advancing army, so they can't live off the land, and they just die in droves. And eventually he returns back to home with 10,000 people from an army of 400,000. Wow, that's just crazy. But there's just so much information out of this. It's wonderful. If you wanted to look at it further, I think there's a Numberphile video that you can Google for it. Just Numberphile and infographic. And you can learn a lot more about that, etc. But there's a lot of ways you can display data. Maybe I can give you some extra credit if you come up with a novel way yourself. Let's see. Let's finish up with a couple more examples. Let me show you a nice little trick that you can do with your spreadsheets. And this is going to be problem number 10 from section 2.3. All right, so let's just, let's see. So I'm going to delete all these, but not these. So problem number 10 talks about the number of home runs hit in a particular year using data from Major League Baseball. And the years start in 1990 and go all the way up to 1993. So I'll type in the first year, 1990, in a spreadsheet. And I'd suggest that you open up a new spreadsheet for this. Don't try and cram it into an old one. Open up a new one. Type in a 1990 there. And the thing is, I don't really want to have to type in 1991, 92, 93, etc. So let's be clever about this. What I'll do is I'll say this cell equals the previous one. So type in an equals, then click A1. And what do I want? I want the next year. So A1 plus 1. And I got 1991. All right, that's great. But I need to continue this for a while. So what I'll do is copy, cut, and paste, right? So what's the control? What do you do for copy? Control C. So Control C or Command C if you're working on a Mac. So Command C, and then we'll paste this all the way down to 24. There we go. So now I got all my years input quite quickly. Now the rest of this is kind of a pain here for you because you have to type in the data. You don't have to type in all of it. Maybe just type in the first 10 here if you want to try and follow along. In 1990, there's 3,317 home runs hit. In 1991, 3,383. In 1992, 3,038. 4,030, so 4030. 94, 3,306. 1995, 4081. 1996, 4,962. Here's where I wish I had a pause button for this video stuff, so I could pause it and just the data would appear. 4,640 in 1997, 5,064 in 1998, 5,528 in 1999. So it looks like baseball players somewhere around here discovered steroids. Just saying. 2,000, 5,693, and then maybe Bud Selig gets a little bit interested in what's going on here. 5,458, 5,059 in 2002, 5,207 in 2003. Is anyone still keeping up, or can I kind of get to the punchline? Yeah, you're still keeping up? All right. Sorry about that for the rest of you. 4,000 or 5,451 in 2004, 5,017 in 2005, 5,386 in 2006, 4,957 in 2007, 4,878 in 2008, 5042 in 2009, 4613 in 2010, 4552 in 2011, two more, 4934 in 2012, and 4661 in 2013. Now, it'd be nice to have a plot of this data in terms of pairs of numbers. So let's again insert a chart to do this, and a nice little time series chart is going to work good for us. So once your data is entered, click Insert, go down to Chart, and I'm surprised it didn't recommend one for us here. Let's see. Let's try a line. No, line chart. That's not. Yeah, let me pick the data first, and then see if that'll help us recommend it. So let's delete this and select the data first. Now let's insert the chart. This should recommend for us a chart. And there you go. You got a nice line chart. So what your job is as a statistician is to kind of summarize what you see. What's happening to the number of home run hits? How would you narrate this story? Starts out in 1990, in the 3000s. Pick up the story from there. Yeah.
I don't know much about baseball, but maybe they changed some of the equipment. Maybe they changed something that's inside the ball to make it easier to hit a home run.
True.
Or as you said, they could have discovered steroids, maybe training.
Yeah. Yeah. So, yeah, a lot of things you could say. Kind of what I was looking for is that the amount of home runs increased till about year 2000, and then it slowly tailed off after that, a little bit. Not as few as in the early 1990s, but not as many as in the late 1990s and early 2000s. So that's kind of what I was looking for. The wheres and whys, I mean, can be conjecture, but you should be able to see the general trend, and that's what the line graph is good for. This is showing you, all right, what's the general trends here? And that's all we're looking for. I think that's about all I need and want to say here. You should be able to do some of this stuff on Google Sheets yourself, and pretty soon you'll be getting an email of an assignment, and once that hits your inbox, I'll probably give about a week to work on that. For now, let me give you some homework. So for section 2.3, homework 1 through 9 and 17 and 19. And that's in the 13th edition. And 1 through 23 in the 12th edition. 12th edition. And like I said, you might run into some problems for which you need to have some data from Triola. So if you do need some data from Triola, it's right here in Desire to Learn. So just go to Triola Datasets and pick up whatever you need. Have a great weekend. See ya.